Hi, I'm Aryan. This is my lab 3 for Physics 2212 at Georgia Tech. The lab explores magnetic field of a bar magnet. First, I'll introduce the purpose and objective of the lab. Then I'll go through some key ideas and concepts and relevant formulae. Next, I'll introduce the experiment and some relevant calculations. Then go through the computational model on GrowScript. Finally, I'll discuss the results of the experimental and computational models and go through some discussion questions. The main objective of this lab is to visually learn and understand how magnetic field works. We'll also understand how distance can affect the magnitude of a magnetic field, and then we'll use the Biot-Savart's law to compare distance dependence measurements. Some key concepts and ideas for this lab. The bar magnet will be treated as a magnetic dipole in this experiment. We'll also need some formulas, the Biot-Savart's law, which gives us the magnetic field due to a magnetic dipole at a given position from the magnetic dipole, and also the distance dependence formula as seen on the screen. This is the experimental setup for the lab. On the left, the setup is required to measure the distance away from the magnetic dipole in the x direction, and on the right, the setup is required to measure the perpendicular distance from the magnetic dipole. We adjust it in a way so that we get the magnetic field equal to 100 microteslas. The setup is important as we are investigating the magnetic field at a given position from the magnetic dipole. This is the data collected from our experiment, which will also be used for our computational model. On the left is the raw data, and on the right is a graph of a natural log of Bx versus a natural log of R. At the bottom are the values for magnetic field at a 45-degree angle from the magnetic dipole. The slope and the y-intercept will be important values which will be used later. Coming to the calculations. So we equate the two formulas for magnetic field as shown here. This allows us to compute the value for mu. This gives us a symbolic value for mu. Then we use the formula with the equation with the natural log in it. The value for n is the slope from the previous graph, which is negative 2.8674. And the y-intercept computes to a natural log of k, which is negative 14.45. Using these values, we compute k, which comes to 5.33 into 10 raised to negative 7. Plugging in the values helps us calculate the value for mu. Now we come to the computational model. The value for mu is given as 2.765. This was calculated in the previous slide. We then use a function to calculate the magnetic field at a given position away from the magnetic dipole. This equation is the last one in the key concept slide. Next, we calculate the strength of the magnetic field at different points around the magnetic dipole, this being the points on axis and perpendicular to it. The perpendicular distance comes up to 0.185. So here are the results of the computational model. The orange arrows represent the direction of the magnetic field on axis, while the perpendicular ones are represented by the 4 blue arrows. The pink arrow represents the one at 45 degrees on the magnetic dipole. The values on the left are obtained from our computational model, and the one on the right are obtained from the physical model or the experimental data. The values have some discrepancies in it. The computational one being 2.44 into 10 raised to negative 5, while the ones from the experimental data average out to 5.5 into 10 raised to negative 5. But since both the values are in the range of 10 raised to negative 5, we can say that the experiment was relatively successful. Observations of the experiment: when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. As the magnetometer moves closer to the magnet, the measured x component of the magnetic field decreases. The position of the magnetometer has no effect on the measured x component of the magnetic field. And lastly, as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. Answering the discussion questions for this lab: what if we hadn't oriented our experiment to compensate for the magnetic north and instead laid out the meter stick at some intermediate angle with respect to Earth's magnetic field? Obviously, Earth's magnetic field would have interfered with the values, and there would have been an inaccuracy in the experiment, giving us different values for the magnetic field at positions away from the dipole. What if we were to stick two identical magnets together end to end and run the experiment? How would you expect measurements to differ? We would end up with the same values for observed locations. However, there would be a scalar component multiplying the magnetic field strength of the magnetic dipole.